Okay, good morning all. So I'm just going to go through what we have done through the semester in a GFA 2024-2025 session, and we have looked at a few topics on adsorption, from definition of adsorption to different types of adsorption that we have. Chemisorption, sorption, that's physical sorption. We considered the definitions and what the differences between chemical absorption and physical absorption is. We look at this slide as well. I believe by now you should be able to differentiate between what an adsorbate is and what adsorption is. If you remember vividly, we looked at this slide and what happens here between gas liquid interface and solid liquid interface. Basically the difference between absorption, that's AB, and adsorption. Okay, so I went on to consider what a monolayer adsorption is, multilayer adsorption, the very characteristics of distillation, adsorption, and adsorption. Yeah, so basically, we also look at adsorbent, the characteristics of adsorbent, and I believe when you went ahead to prepare for your book presentations, I'm sure you have met, from the industry perspective, the the varying characteristics of adsorbent as applicable to different processes that you all considered in your group presentation in terms of size, the density, the porosity, the size distribution. We looked at charcoal. We considered silicone gel, zeolite, activated carbon. Basically, we look at um, this profile that we have here. So by now, you should be able to you should understand the behavior of zeolite, your silicone gel, and activated carbon. Okay, so moving forward, we look at the types of adsorbent, the activated alumina, silica, zeolite, activated carbon, polymeric adsorbents, and a whole lot of others that you also presented during your group presentations. Okay, application of adsorbent, we look at different um, industrial application of these adsorbents. What are their peculiarities? What are their challenges? Um, when you have a process that you need to undergo adsorption in the industry, how do you choose based on the characteristics of the adsorbent, based on the prevailing industrial conditions? Okay, so all these things play out. You have to consider them within your team, okay, before you eventually settle for the type of adsorbent that you are going to choose. And don't forget the process, the peculiarity of the process itself, the adsorbate that is involved, okay, the medium, the equipment that we are going to be making use of. Okay, so all this in designing your adsorption process. So all this come to play. Okay, so adsorption selection, we look at some few characteristics that makes some peculiar adsorbents commercially attractive. Okay, so in terms of the large internal surface area, the accessibility, availability, few of the groups also discussed adsorbents that can easily be regenerated, bioadsorbents, and the like. So, and the fact that the adsorbent doesn't age rapidly, it is mechanically strong. All these are commercially desirable characteristics of your choice. Okay, um, when it comes to the choice basically of adsorbents in industrial processes. Okay, so we'll also run through um, this exercise as well. Okay, so I believe you should have laid your hands on this exercise. Please do if you have not. So this basically looking at carbon A and carbon B, and which one would be your best selection. Okay, which of these adsorbents, okay, will be your best selection, okay, based on the few characteristics which are stated in the question. So it's solved here. Please go through it. Okay, so the adsorption of each species proceeds as pure gas adsorption occurs. Then we have the breakthrough, which occurs through the detection of adsorbate presence in the effluent. Okay, so what that is saying is you have a breakthrough that happens immediately your adsorbate starts um, occurring, you sense the presence of your adsorbate in the effluent, then you know that possibly at that point your adsorbate has been used up, because ideally you're not supposed to find your adsorbate. Okay, it's not supposed to be in your effluent, but the time your adsorbate starts occurring in your effluent, it shows that there is a breakthrough point, meaning that your adsorbent are possibly be used up at that point. So there could be a reloading, you can halt the process, so many other things that could be done. So here is saying that which of these, okay, these are the gaseous species, um the adsorbates, and these are the adsorbents. So you have carbon A and carbon B and the loading that you have on them. So which of them would you choose? Okay, or would you recommend for your company? Okay, based on the prevailing operating conditions that are stated in the question. Uh, okay, so please look up this. I think we discussed this as well. So please look up this exercise and be able to differentiate based on the profile, zeolite, silicon gel, alumina, carbon. Okay, so based on the profile, the isotherms that are stated there, we discussed that intricately during the class. So please, you can go back to the video and listen to it all over. Okay, so and we also touched isotherms, the different types of isotherms that we have: Fredluke, Langmuir, Betz, Gibbs, and some other ones that were not mentioned, because the four are the basically common ones, okay, that we have in literature. So we looked up adsorption equilibria, what that is about, and how isotherms are developed. Okay, we also look at this, the monolayer section and the multilayer formation, based on the difference between um, the formation of monolayers and the formation of multi-layers that I stated earlier at the very beginning of the class is applicable at this point. So I'm sure you can still recollect the formation of monolayer and what happens when multi-layers are formed. Okay, so we look at how these equations are generated, okay, then different types of isotherms that we have, and the behavior of each isotherm, how each of them are formed, the ones that have monolayers and multi-layers, and the ones that have basically only multi-layers only. Okay, so look up each of these type, each of these isotherm type, okay, and try to understand. I believe we have done this, okay, but still go through it. Try to understand the try to understand the formation of the monolayers and the multi-layers as well. Okay, so for type 1 to type 6 rather, you have all these characteristics features which describes the different types of isotherms, both multi and mono, that are described in the previous slide. So please look through them. The major characteristics of Langmuir isotherm, which is one of the basic foremost isotherms that have been generated in literature by Irving Langmuir. Please take note of all the four hypotheses of Langmuir, of the Langmuir isotherm. Take note of it. What are the characteristics of the single layer adsorption isotherm of Langmuir? Why is it valid at low temperature? Okay, so take note of all that. Okay, we discuss all this. Please try to run through your slides and understand them. From there, we cross to bed isotherm. Okay, and this specific equation, try to understand it. This represents y equals mx plus c. I think I gave you an assignment on an exercise to complete it. I think I explained it up to a point and I asked you to do the plot, okay, of the bed isotherm. Then we moved over to the gifts. So basically for your Langmuir, your beds, and the gifts, please understand their assumptions, their equations, their applications, specifically to industrial processes. Okay. Then we cross over to multi-component adsorption. Okay. So some few multi-component adsorption isotherm, the extended Langmuir isotherm. Understand the adsorptions. So be able to differentiate between the adsorption of Langmuir when it's considered single component at isotherm, and the adsorption that was put forward by the time Langmuir isotherm was extended to multi-component process. Okay, I hope you understand that. So what I'm trying to say basically is be able to differentiate between the adsorption of Langmuir to single component and multi-component adsorption. Okay, Frederick equation as well. Redlich-Peterson isotherm. So you can read up all these. You can read up them. Then the interaction effect, we also discussed it can be synergistic, antagonistic, and you may not have an interaction occurring. Okay, so I'm going to go straight up to our potential theory for today. And we're just going to spend a few minutes looking at what potential theory is all about. So if you have the soft copy of your notes, you can as well bring it out and follow up from it. Just a minute, please. Please, can you hear me? Can someone confirm you can hear me?
I can hear you, ma'am.
All right.
Can hear you, ma'am.
All right, thank you. So, so basically for potential theory, is the postulate of that was put forward by the great scholars, okay, in order to describe the presence of a fixed volume, okay, to the absorbing solid surface. So what they are trying to say is that adsorbed layers can be considered to be contained in an adsorption space. Like we can have a space between the adsorbent and the adsorbate. Okay, if you consider the diagram that we have here, you have the adsorbent, and then you have the adsorbent and you have the adsorbate, and in between you have a space that behaves like a liquid form. Okay, so this theory was postulated by Pauling in 1914. So what he regarded is that the potential of a point within that adsorption space is a measure of the work carried out by surface forces. So this is all about forces which Pauling considered to be occurring between the adsorbent and the adsorbate. So describing that in between these two surfaces, it's trying to say that in between them, there is no close physical contact, that there is an imaginary liquid phase that occurs between the adsorbent and the adsorbate. Okay, so this is all about the surface forces, which brings one molecule of the adsorbate to that point from infinity, or a point at such a distance from the surface that those forces exert no attraction. So what's trying to say basically is that there are forces that bring um, uh, a one molecule, okay, of the adsorbate from its point to in between this space, and then the adsorption actually occurs. But these surfaces tend to, he sees that they tend to exist between the adsorbent and the adsorbate. And his theory, like I said, is that he generated this potential, the potential of a point that exists in this absorption space. So he says, okay, this potential that occurs with this absorption space, this space that occurs between the adsorbent and the adsorbate, that is a measure of work carried out by surface forces. And what does the surface forces do? They bring one molecule of adsorbate to that point from infinity. So if you have your random movement of your adsorbate, in this case, a gas phase. I think they also applied it to liquid phase. So in this phase, a gas phase. So he's saying from infinity, you bring that, there is a work done in bringing one mole of the adsorbate from infinity to a distance from the surface, that's from the adsorbate, such that all the forces exert no attraction. So from that, at that point, there is a surface, there is a space, and if that one mole of adsorbate occurs within this space, there is no there is actually within the absorption space, so absorption can occur within this space, but it's saying that there is no exertion of an attraction so the work carried out depends on the phases that are involved, whether you have your liquid phase or your gaseous phase in contact with your solid phase, which is the adsorbent. So basically, the three possibilities that he looked at in terms of all the forces and the seemingly uh, liquid layers that occur between your adsorbent and your adsorbate, okay, is that there can be occurrence of the temperature of the system below the critical temperature of the adsorbate, and the adsorbed phase could be regarded as a liquid. So what that is saying that if the temperature of the system, the whole system itself, is below the critical temperature of the adsorbate, the adsorbed phase will behave as a liquid. Okay? And if the temperature is just below the critical temperature of the adsorbed phase, uh, critical temperature of the adsorbed phase, what happens? That phase will be a mixture of both vapor and liquid. Will be mixture of both vapor and liquid. And if the temperature is above the critical temperature of the adsorbate, what happens? The adsorbed phase will be a gas. The absorbed phase will be a gas. So the first point, that's the point A, has been considered as the simplest and most common. So we have the space in between the adsorbate and the adsorbent behaving as a liquid. Okay, and that's what we have in this diagram that we have on this slide. So at temperature below the critical point, the pressure at the adsorbent surface is the saturated vapor pressure of the liquid adsorbate. That's your P naught. Okay. So at the limit of adsorption space, the pressure exerted by the adsorbate molecules in the gas phase is P. So for an ideal gas, you have the work done given by your epsilon P, your RT as your gas constant temperature limit. That's your vapor pressure by your gas phase pressure. Okay, so here we have the gas phase, the adsorbent. If the temperature is for A, the temperature, we are considering that the temperature of the system is below the critical temperature of the adsorbate. So the adsorbed phase is regarded as a liquid. Okay, just a minute. The adsorbed phase that you have here in between behaves as a liquid. So for that, this equation holds for an ideal gas. So if you have an ideal gas existing here, okay, so you use that as an experimental uh, for the postulation of this theory. Okay, so the potential theory specifically postulates a unique relationship between the adsorption potential and the volume of the adsorbed phase contained between the equipotential surface and the solid. This is the equipotential surface here, the surface that behaves as a liquid. Okay, that's the equipotential surface. And don't forget that he also regarded that there are forces that act on the um, 1 mole adsorbent that is brought from infinity into here. Okay, so when it behaves like a liquid, what do we have? He postulated a unique relationship between the adsorption potential and the volume of the adsorbed phase contained between the equipotential surface and the solid. Okay, so here you have your epsilon V is a function of your V. It's a function of your V. So if you also check your notes, the soft copy notes that I gave you, you see your V volume of the adsorbed molecules in its liquid-like state per unit adsorbent mass. That's on page 30. On page 30. Okay, I think that's basically the last statement on page 30. Okay, so your V is the volume of the adsorbed molecule in its liquid-like state per unit adsorbent mass. Okay, so you know every other thing that your RT ln P naught over P, okay, stands for. So if you have this and then you have it plotted, this is an experimental procedure that has been carried out for adsorption potential. This is the adsorption potential epsilon P that we have here in equation 2, epsilon P. Don't forget your equation 1, your epsilon P for an ideal gas. Okay, work done in bringing a mole to the adsorbent surface. Okay, so it's given as this. So for Polaine, he then postulated this equation 2, that this epsilon P work done in bringing 1 mole of the adsorbent surface, in his case from infinity now to that equipotential surface, okay, liquid-like surface. What happens? You have, it says, is equal to its function of V. And don't forget what I said V is. Okay. So where the function of equation 2, the function that's the equation 2 is independent of temperature, what do you have? You can combine your equation 1, this is equation 1 here, with equation 2 to give an adsorption isotherm. Okay, so you have this plot. If you have your RT ln P naught over P plotted against your V, V is volume occupied by gas, So just a minute, please. Okay, so V is your volume occupied by gas adsorbed at potential greater than your epsilon P. So in this case, the volume is 10 raised to power 8 meter cube per kilogram. You have the varying temperature at 199, 196.6, 273.1, 303.1, 353.1, 424.6. So all these were plotted against the adsorption potential. Okay. So for this, when you have the volume occupied by gas, excuse me, when you have the plot of this V against RT ln P naught over P, don't forget that this is your epsilon P plotted against V. When you have it plotted against V, okay, what happens is you have generated an isotherm profile, okay. In this case, CO2 is your adsorbate, charcoal is your adsorbate. So, and these were plotted at varying temperatures. So what this is saying that this is valid. Let me edit it so that you can see what is written here fully. Okay, so what this is saying is that this curve, this isotherm curve, is valid for charcoal and CO2 at any temperature. Okay, so its validity may often also be extended to other adsorbents on the same on to other adsorbents. Okay, so this should be on the same profile. Okay, so this profile can be extended to other adsorbents. Okay, that's basically what this is about. The same profile, isotherm profile. Okay. So what this is saying is that if you have varying temperatures, you can actually measure from here. You have the adsorption potential, you have the equations of your adsorption potential. So you can fix in the temperature, the pressure, and then you can very invariably calculate the volume occupied by gas adsorbed at potential, okay, at different potential. Okay, so you can also read it from here. For instance, at 20 Hp epsilon P adsorption potential of joule per kilomole, what do you have? If you come somewhere here, okay, so somewhere here, what temperature do you have? This temperature, that's about at 303 Kelvin. So you can read it down, okay? So these are 303 Kelvin. So if you have temperature, especially the ones that are within this range of temperatures, okay, if you are carrying out an adsorption, okay, within this range of temperatures, you can actually come here, okay, and have be preformed of what your volume is likely to be, the volume of the adsorbent that is likely to be adsorbed, okay, given your adsorption potential. An absorption of potential of 10 at this temperature, this also 303 Kelvin. Okay, if you come here, if you extend it here, an absorb potential of 10 at this temperature, this is 353 Kelvin. Okay, so you can measure out what the volume could be. If you come somewhere here, let's say this is about 9, thereabout. If you trace it down to this place, if you have a temperature of 273 Kelvin, you can read out what your um, volume, the volume of your adsorbent that will be adsorbed would likely be. Okay. If you want to check the volume, what the adsorption potential can be at 273 Kelvin, what adsorption potential can be at 273 Kelvin. So you have um, absorption potential at 273 Kelvin. You can look up, okay, and at, let's say, a volume of 20 or less than 20, okay, here you have 273 here, 20 here, a volume of 20. So we have something close to 20 here, somewhere here, and you have 273 Kelvin. So you can read out what your absorption potential is likely to be. And if you have the absorption potential and the varying temperatures, you can as well read out what the volume of the adsorbent is likely to be. So Poline actually developed this process, this kind of unified profile, so that if you have at any temperature and you have the same adsorbent and adsorbate, you can read up from this profile, okay? And it can also be extended, okay? You can be extended to other adsorbents as well. So if you have, this is basically for charcoal and CO2. So probably before you carry out your experiment, and then if you have a basic understanding of what your the adsorbent experiment you are about to carry out, okay, because you have to carry out the pilot test before you scale it up to field conditions. So if you carry it out and from your basic understanding, if you see that, oh, okay, the behavior of your CO2 and the behavior of your adsorbent and adsorbate is likely to be similar to that of charcoal and CO2. And you know that there are also other conditions that may or may not come to play in this wise, okay? Uh, like your pressure, your column, the weights, um, if the gas you are considering is corrosive or not, um, rate of flow, your inlet, your outlet, and all that. So there are so many other prevailing process conditions, okay? But in this wise, if you are carrying out a pilot test, you can actually check if your adsorbent and adsorbate you are considering have a similitude of charcoal CO2 characteristics and interaction, okay, based on their adsorption characteristics. So you can actually have a foreknowledge of what the volume of your adsorbate is likely to be. So that is why it's said by Poline that when you generate the profile at these different temperatures, it can be used at any other temperature. You can check for at any other temperature, okay? And then you can as well still make use of it for some other type of adsorbents that have close characteristics to what you have earlier developed. Okay, so that would be a short one on polar theory. I want you to look up other videos on the potential theory as relates to adsorption. It's quite an interesting one. Further, I would like you to also look up related videos on YouTube. Look up your soft copy materials and all the exercises contained in it. Look up past questions, and then your group presentations. Please try as much as possible to master the subject matter uh, of your group presentations. Okay, so yeah, so I would listen to comments and questions.
Good morning, ma.
Yeah, good morning.
Yeah, I have a question, although it's not on what you just discussed today. I was thinking that if we are asked what are the types of adsorption, I know that we have a single component and multi-components. We also have monolayer and multi-layer, and we also have physical and chemical adsorption. So if we are asked what are types of adsorption in test on our exam, like what should be the answer to that question?
Well, if you asked the type of adsorption, the term will be stated so that you know what to write. Okay? There'll be
Okay,
a caveat to the question. Maybe it's in time of the process, adsorption process. So a caveat will be added to the question so you know what exactly the question is pointing towards.
okay, ma. Okay.
So I gave you an assignment. I don't know if there are one or two people that did the plots over the holiday. You're supposed to do the plots. Yeah, the exercise on spherical particle of 15 nanometer diameter and density 2290 kilogram per meter cube. I'm reading from your page 25. Spherical diameter of 15 nanometer diameter and density 2290 kilogram per meter cube are pressed together to form a pellet. The following equilibrium data were obtained from the sorption of nitrogen at 77 Kelvin. Obtain estimates of the surface area of the pellets from the adsorption isotherm and compare the estimates with the geometric surface. The density of nitrogen at 77 Kelvin is 808 kilogram per meter cube. So you're given the density of liquid nitrogen, 808 kilogram per meter cube. Area occupied by one adsorbed molecule of nitrogen to be 0.162 nanometer squared. Your Avogadro number, 6.02 times 10 to the power 26. So please, how many of you did the plot? Did anybody attempt plotting it and obtaining your intercept and your slope? Your intercept and your
Ma,
slope.
I plotted it, but I don't know if my answer was correct because the intercept was below the zero line, negative. So I don't know if I'm correct. I don't think I'm correct because in the answer was there. I think 13 or something like that. So I didn't get the correct answer.
And you should try to understand and plot it again. Okay, just hold on. So who else attempted the plot? Who else attempted it? You have your bet isotope is y equals mx plus c. Okay, your c is 1 over v prime b, and you have your mx, that's your b minus 1 into p over p naught. That's your m, your slope, and your x is 1 over v prime b. Okay, so you have it already. You have your p over p naught. You have your p over p naught. So all you need to do is to estimate p over p naught divided by your v into 1 minus p over p naught as your y. Okay, so and then do the plotting. So it's quite simple. Yeah, did anybody attempt it? So that will be part of your CA. I want you to attempt it uh, since nobody did it over the holiday. So I want it by Friday. You attempt it, do the plotting on your Excel, and forward it to me. Forward it to your I think okay, you can do the plotting on Excel, copy it, put it on a worksheet. Then your class rep collates them all on a single Word, either Word or Excel. You can use any one. So you put your name and your matric number. Your name and your matric number. Because this is one of the exercises that you actually need to plot in class. You need to do the physical plotting in class so that you understand how bed isotherm works. Okay, but because you're having the online class now, so it shouldn't be an hindrance to you actually laying your hands on this. Okay, so um, did anyone else attempt it? Whether you got the answer or not, did anyone else attempt it? Nobody.
I
How
did.
many people on the call? 29 people. Nobody.
I did.
Okay, Percy. Okay. Yeah, so go on, Percy.
Yes, I attempted it, and I think what I got is very close, but not exactly, ma.
Okay,
But I think it's
fantastic.
within the limit. Yes, ma.
It's not necessary that you got the same answer because you are making use of a graduated sheet in your graph plot. So, or did you use Excel? Did you use Excel sheet or you did hand
No, ma,
plotting?
I plotted it manually.
Okay, okay, fine, fine. Okay, so what was your intercept?
I had 13.1.
Okay, no, I'm asking for your intercept now. Your 1 over V prime B, your
Okay,
intercept
my,
and your
my
slope.
I got 270 something, sha.
Okay, what about your slope?
My slope, I had 13.100.
Okay, okay, fantastic. So were you able to estimate your B and your V prime?
Yes, ma.
Okay. So do you have the value for your B and your V prime?
My work is not here, but I remember I got 45 point something for B. Then for V prime, I had around 60, I think around 62 exponential minus 6.
Okay. And you were able to estimate your total surface area?
Yes, ma.
Okay, fantastic. So that's all I need to know. So you were asked to calculate the total surface area for that. So please, if you have not done it, I need to have it by Friday. I need to have it by Friday. I know you all are in different locations, either in Nigeria or outside Nigeria, okay? And maybe those that are around and you feel you can do the hand plotting in the graph and bring it to school, it's fine. If you know you're around school and you can do that, fine. But if not, please do it on your Excel sheet. Send it to your class rep or your assistant class rep, and then she collates it in just one Excel sheet. I want just one Excel sheet. So you collate everything in just one Excel sheet, including name. You open the different Excel sheets for each person, name and matric number. Or you may not include your name, just your matric number is fine. Make your matric number very bold so I know which plot it is. Then I want to see your calculations as well. Okay, so I'm glad somebody attempted that. Please, that's exercise one. We also have one or two other exercises for those that were asking after exercises. Please, you have more than enough exercises. Please go through them. Most of them are already solved. Please go through them. Go through them. Okay. I think we have discussed this first exercise on page 30, 30 up to 33. We've discussed that in the last class. The one for calculation of specific surface area. So if I ask you a question in hindsight that why is the specific surface area characteristics important in the choice of an adsorbent? Now you know from these calculations on estimation of specific surface area. Okay. For the one I asked you to plot under base isotherm, the total surface area was asked to be calculated. Okay. And then you're asked to obtain the estimate of the surface area of the pellets from the adsorption isotherm. So the plot that you did is the adsorption isotherm. Percy, were you able to identify that the plot you did is an adsorption isotherm?
Not really, ma.
Why? How did your plot look?
It looks like Langmuir isotherm, kind of.
It looks like what?
Yeah, like a straight line, then kind of a curve a little bit though.
Yeah, that's an adsorption isotherm. You've forgotten how your Langmuir isotherm looked like?
Yeah, that's what I said, but it looks like it.
Okay, okay, fantastic. So that is your isotherm. It says, the question says, obtain the estimate of the surface area of the pellet from the adsorption isotherm and compare the estimates with the geometric surface area. Okay, so please finish that question. I've treated the first part. You have the equations here. I know some of you are waiting for, oh, she's going to give us all the equations. She'll give us all the equations, and then we just slot in. No, the questions can come in any form. Please go and treat the past questions so far. It can now come in any form, so get yourself prepared. Okay, and then the chapter 17 of your Richardson and Colson, the one we are making use of for this class. Has anyone tried to look up the exercises therein in the chapter 17? Anybody? So look up the exercises that you have under your chapter 17. Okay. Some of them are similar to what we have already treated. So your question can come in any form. I'll still try and see if I can do maybe one or two more videos for you. But from next week, Dr. Adeboye will take over. So please, if you don't understand anything, as you read, you can reach out to me. Okay, so Richardson and Coating, if you check page 231, section 217, on your Richardson and Coating, page 231, section 17, section 217, section 217. Okay. So quickly before we go today, if you have questions and comments, please. So I just created breakout rooms for us. I want you to go to your rooms. So what I want you to do basically in your rooms, I'll be marking attendance in each room. So this is my last attendance. So what I want you to do basically in your rooms is to discuss what you have learned so far. What you have learned so far in this course. And then you are going to, within yourselves, what you have learned so far, at least 3 to 5 points. And then I'm going to be listening to them. Okay? I'll be taking notes. All right.
Like I joined this breakout room before.
Yeah, I mistakenly did that too. So I'm opening the meeting back on that tab.
Okay.
I'm coming.
Okay, so I'm in a room presently. How many people do I have here? 3 people. Can you hear me?
Yes, ma'am, we can
Yes,
hear
ma'am.
you.
we can hear you.
Oh, okay. So the 3 of you, I have David Aderomu. Please give me your first two numbers of your matric number, and I think the last. Yes, please go on fast, quickly, please.
First two are 1-8, last two are 1-3.
Okay. Yeah. Next person. Is this Aderomu's group? Can you hear me? Who is in how many people are in this group?
4.
I have 4 people here.
Okay. Okay, please, can you give me your surname? Your surname only.
Adejola.
Okay, Adejola. Please, I want you to speak up as quickly as possible.
Adejola.
Jai Obama.
Yeah. Jayoba, yes.
Usholale.
Yes.
John Ma.
Okay. Yes.
That's all.
Okay. So 4 of you. All right. So what have you learned so far in this course?
Ma, I learned about adsorption, equilibrium, and isotherms. Isotherms are the relationship they're like the relationship between the adsorbent and adsorbate. They show the relationship between adsorbate and adsorbent, and they also show the adsorption equilibrium relationship.
Jayoba.
Man, good morning, ma.
Go on, please.
Okay, I've learned about the adsorption process. Of course, about the monolayer adsorption, where we have a single layer of molecule that the adsorbate that is attached to the surface of the adsorbent, and also about the multilayer adsorption, where you have a molecule of the adsorbate not only adhering to the surface of the adsorbent, but also forming additional layers on the initial monolayer. And I also learned about the physical and chemical characteristics of adsorbents, which are the adsorbent size, the
Okay, thank
adsorbent.
you. Osholale.
Yeah, good morning, ma'am. So I've learned about adsorption, what adsorption is, types of adsorption, physical, chemical adsorption. Learned about the differences between adsorption, distillation, fractionation, and then also I've learned about different types of adsorbents and
Adejola.
Good morning, ma. So I've learned about adsorption, the types of absorption, the key properties of absorbents, difference between adsorption and absorption, also the factors that influences adsorption, and also the Langmuir, the Betz, isotherms. The isotherms basically the shape of the Frederick, and also the group project that has made me like um diversify, and also made me learn about the future of adsorption regeneration, what it is about the regeneration of adsorption.
Okay. All right, well done. So do you have any question from your group?
No, ma.
Okay. All right, so you can go back to the main room. Um,
Ma, can you hear me?
yes.
Someone just joined. Oh, let me see.
Oh, the person is late. He was not in class. Hello, can you hear me? Can you hear
Yes,
me,
ma'am.
please?
Can you hear me?
Okay, so
Yes, ma'am.
please give me your surname quickly, please.
Salau, Salau.
Okay, Salau, you are the only one in this group.
Amondi,
No, there are other people.
Please, I don't have luxury of time. Please speak up. Give me your surnames if you are there.
Amondi, ma. Amondi.
Amondi, yes.
Yeah.
So like, I have Salau and Amondi only in this breakout room.
Ma Aderomu, but you've already taken my name before.
Salau, Amondi, and Adirum. So what have you learned so far in this
And
course?
Vianana. Vianana, speak up. One more
What have
person
you
to
learned so far
Vianana.
in this course? I have 3 names with me that spoke up. What have you learned so far in this course? Salau.
Okay, ma. Let me just talk. So I learned the project I worked on, which is regeneration techniques of adsorbents. And the first one I'm talking about is thermal regeneration, which involves the use of high temperature to dissolve adsorbates from adsorbents. Then the next one is chemical regeneration, which involves treating adsorbents with acid, alkalis, or solvents to remove adsorbates. Then I'll be talking about steam regeneration,
You have 30 seconds.
which involves using high pressure steam to remove volatile organic compounds or other contaminants like diazobates. Then there are other techniques too, like microwave assisted regeneration and biological regeneration. That one involves using microorganisms to degrade, absorb organic contaminants. So thank you.
Adirum. Amondi.
Ma,
Amondi, go on.
I'm done. You said I have 30
Oh,
seconds.
okay, sorry. Salau,
Okay, ma. So far I have
30
learned
seconds.
okay, ma, the process that is adsorption and linking it to the group project that was assigned to us. We worked on the use of adsorption in cleaning of oil spills. So we looked at how adsorbents are employed in situations where other materials could not be used to clean up the oil spills, and we looked at the Deepwater Horizon spill that happened in 2010 and the um Deepwater Horizon oil spill, and how they made use of dispersants, silica gel, and many other things to clean up after the explosion, which helped in minimizing the environmental effects and the damage to wildlife, to sea life, to the environment,
Okay.
basically.
Please, I want what you have learned in class, first of all. What you learned in class, because your examination is going to be centered around that. But I'm done with your group. All right, so you can join the main room. Go back to the main room.
Ma, I've not spoken, ma.
You are late.
Ma, I've also not spoken.
So,
You are late. You joined the group late. I had for
no,
surnames
I
immediately I
didn't
got
join
there.
late.
You are late. How many people are in this group? Hello, everyone.
Hello, ma'am.
How many people are in this group? I have 1 minute to spend in your room. How many people are in this
Yeah,
group?
we are
Give me your
we are
surname.
formal.
Give me your surnames in succession, please. Quickly.
Uduma. Onuzo.
Elijah.
Korodele.
Orobele.
Korodele.
Okay, Korodele. Onuzo.
Yes, ma'am.
Okay. So, what have you learned so far in this class? 30 seconds each. 30 seconds each. If nobody speaks after 5 seconds, I'm going to another room and I'm scoring all of you 0.
All right, ma'am. So I learned about the potential theory, which was devised by Polanyi, and how he related the theory with temperature and critical temperature of the adsorbent and the adsorbent phase.
Okay. Is this your first class?
No, ma'am.
Okay. It seems what you learned is only centered around the last class.
No, I was listening. I paid attention to your class when we were talking about when
In
scholars
this
brought
course.
about.
In this course. Okay. Korodele, go on. What have you learned so far in this course? Korodele.
Good morning. Okay, so the different type of adsorption, the different type of adsorbents, and when they are being used. So and also the um current trends of adsorption processes in Nigeria industries. Because majorly it was more of what me and my group member worked on.
Okay.
Thank you.
I did not say what you have learned from your group project. I mean, this course specifically. What I've been teaching you so far. What have you learned?
Yes,
Uduma.
ma.
Elijah, please go on.
Good morning, ma. I've
Go on,
learned
please.
about absorption, the adsorption isotherm, the graphs, and also the types of isotherms we have: the Langmuir isotherm, Freundlich, Beth, and Gibbs isotherm. And today I learned about potential theory in your class. I also learned about different types of absorbents to use and their properties, and the types of absorbents too.
Okay. Uduma, have you spoken?
No, I've not spoken. Okay.
Go on, please.
Onuzo, ma'am. For mine,
I learned about the first this thing. We learned about the types of absorption, like the physical absorption, physiosorption, and the chemical absorption. Then after that, we talked about the adsorption isotherms, the type 1, type 2, and so on, the Langmuir isotherm, and the factors affecting adsorption. We talked about the surface area. Then later we talked about the absorption kinetics, the applications of absorption,
Okay,
and
thank
after
you.
that,
All right, thank you. Uduma, have you spoken?
Yes, ma, I have. I
Okay,
spoke yes.
so I have Uduma, Eleja, Korodele, and Onuzo. Please join the main
yes, ma'am.
room.
All right, ma.
Okay, ma'am.
Okay, so how many people do I have? Hello, how many people do I have in this room? I have 1 minute to spend in this room. How many people do I have in this room? Okay. Is there anyone in this room? Is there anyone in this room? Can you hear me?
Yes, ma'am. Good morning, ma'am.
Your surname, please. Good morning.
Ogunleye, ma'am. Miracle.
What have you learned so far in this course? I have 30 seconds.
Oh, okay, ma. So I've learned about adsorption, the single layer, multi-layer components. I've learned the technical processes in adsorption, and then the innovations, which is what my group actually worked on. I know the isotherms. I'm still reading. Going through the exercises that are in the slides.
All right. So please go through the exercises, do your plots, and submit your assignments. You can go back to the main
Yes,
room.
ma'am. Okay, ma'am.
Hello, anyone in this room? Hello, anyone in this room? Hello, anyone in this room? Hello, anyone in this room?
Yes, ma.
Yes, ma'am.
Okay.
Yeah, ma'am.
All right. So please, your surnames. I have a minute to spend in your room. So, and I need your surnames and what you've learned so far in this course. The theoretical aspect, not the group presentations. What you've learned so far in the theoretical aspect. But please give me your surnames quickly, please. Your surnames.
Akapo.
All right.
Nwose, Nwose.
Okay. So I only have Akapo and Nwose in this room. Okay, so Akapo and Nwose.
Osai.
Ma, I'm dealing with network. Can you hear me?
Please, I don't have all day.
Can you
Your
hear me?
surname, please, if you can hear me.
Osai.
Osai, yeah. Any
Ojito.
other person?
Ojito. Can you hear me, ma? Ojito.
I'll advise you project your voice and
Ojito.
speak up. So, Akapo, what have you learned so far in this
Ma,
course?
let me type it. Ma, let me type it.
Akapo, what have you learned so far in this course?
Okay, good morning, ma.
You have 5 seconds.
So I learned the definition of adsorption, which is the adherence of gas or vapor to the solid to a solid phase that is called the adsorbent. And the gas or vapor is called the adsorbate. I also learned that there are types of adsorption. We have monolayer adsorption, we have multilayer adsorption, and in monolayer adsorption, in adsorption generally, desorption takes place at the same time simultaneously with adsorption. You also taught us isotherms.
Okay. Who wants to continue?
Okay.
All right, ma.
5 seconds.
In addition to what she mentioned, you also taught us about isotherm, where we have like near isotherm, Beth isotherm, Friedrich isotherms, and the rest of it. Then we did a lot of calculations around the Beth isotherms. You also told us how we can select a particular isorbent based on some of their characteristics, such as surface area in particular, density, and the rest of them. Then
All right.
today
Osai.
Yes.
Osai.
Yes, ma. So I learned in this course that adsorption is a surface phenomenon, while absorption is a bulk phenomenon. And then isotherms help us to characterize the adsorption. Sorry, I'm having. Sorry, as isotherms are important when dealing with multi-component adsorption, and then they help us to know the nature of the adsorption.
Okay, so I believe you need to read more to grab the concept well. Okay, so I don't have all day. Please go back to the main room and tell if there are people in the main room that I'm yet to visit their breakout room. Please tell them to go back to their breakout room. You can join the main room.
Ojito, ma. Ma, can you hear me?
All right, ma. Thank you, ma.
Thank you, ma.
Hello, anyone in this room? Hello, there are people in this room?
Yes, ma.
Okay.
Good
Okay,
afternoon, ma.
okay. I've been to this room. Have I been to your room before now? Uzoma.
No, ma.
Okay. So please give me your surnames. I have a minute to spend in your room. I want you to tell me what you have learned so far in this course, not the group presentation, but what you have learned in the theoretical aspects of this course. So please give me your surnames quickly, please. We have just 1 minute. Your surnames.
Uzoma.
Adeni. Guru.
Oyekomi, ma. Oyekomi.
Usho. We should write it down.
Okay, so I have 4 people: Uzoma, Adeni, Duru, and Oyekomi. Please go on, Uzoma. You have 5 seconds.
Okay. Okay, in this course, I learned that we have different types of adsorption depending on the when you talk about types of adsorption, depending on the number of layers, we have what we call monolayer and multilayer adsorption. Then in monolayer adsorption, all the adsorbed molecules are in contact with the surface layer of the adsorbent. While in multilayer adsorption, the absorption space accommodates more than one layer of the molecule, and not all adsorbed molecules are in contact with the surface layer of the adsorbent. We also have
Okay,
what we call
Adeni,
physical.
go on, Adeni.
Yes, ma'am. So I learned about the differences between your adsorption, your absorption, and distillation. So your adsorption is a surface phenomenon, is a non-steady state process. Your absorption is a bulk phenomenon, is a steady state process. And distillation depends on volatility to proceed, and it requires it, unlike your absorption and your adsorption. Then I learned about interaction effects, where you have multiple components in your fluids. So if it's improved, you have our synergistic when your adsorbate is improved by multi-components. Then we have your non-interactive when your multi-component doesn't affect how your adsorbate absorbs fluid. Then the last one, when your adsorbate is reduced by the amount of multi-components in it, we have your antagonistic. Then we also have different types of adsorption equilibriums. You have your BAT and your Langmuir. So your Langmuir, it cannot form multi-layers, it forms monolayers, unlike your BAT that there's formation of multi-layers. Then in your Langmuir as well, it assumes that the surface of our adsorbent is uniform. So uniform
Okay,
absorption takes.
Duru, pick it from there. Duru, go on.
Oh,
What have you learned?
okay, yes, ma. Yes, ma. Starting from the beginning, I learned the basics of adsorption, the mechanism involved, and how different it is from absorption and distillation. Then going on, you talked about the types of adsorbents and their application. Then I also learned about the type 1 to type 5 adsorption equilibria isotherms and the formation of non-porous monolayers and multi-layers and how graphically different they look. And I learned about the isotherms, the Langmuir isotherm and the beta isotherm.
Okay, Oyekomi.
Hello, ma. So during the course of this course, I learned absorption. I learned the difference in why the factors we consider when selecting the separation process between absorption, and this distillation, the absorbent types, the different factors we have to consider, their size, the density. I also learned the type 1, type 2, the type 3, the absorption, the equilibria, then also the isotherms, basically the four major isotherms, and when this multi-component the multi-component absorption isotherms also. So yes, ma'am.
Okay, all right. Thank you. You can go back to the main room.
Okay, ma'am.
Thank you, ma.
Okay, do I have anyone in this room? Do I have anyone in this room? Room 2. Is anyone in this room? Ebenezer Arifalo, are you present? Okay. Seems you are not present. Okay, hello everyone. Can you hear me? So thank
Yes,
you.
ma'am, we can hear you, ma'am.
Yes, we can
Yes,
hear you,
ma'am.
ma'am.
Yeah, thank you very much. It has been a wonderful one. Adejola, Jayoba, Ushiolale, John Esther, Salau, Amondi, Aderomu, Uduma, Eleja, Korodele, Onuzo, Ogunleye, Akapo, Nwose, Osai, Ojeto, Uzoma, Adeni, Juru, and Oyekomi. So I think about 22 of them participated, were active. Some people have only their phones or their laptops connected and they are not active in class. They are not even present.
Hello, ma. Hello, ma.
So some were also not available to join the breakout sessions. And some were in the breakout sessions are called out their names and they didn't respond. Okay, so these are the people that were active, joined the breakout sessions and were active in their session. And
Hello, ma. I was not able to join the breakout session. I got locked out.
I put you in breakout sessions. Many of you, I think maybe your colleagues reach out to you and then you joined the class. You joined the link. So please. So congratulations to everybody that was available, was active in all the breakout rooms. Thank you very much. Please, if you have any